So let's go to number 13. All right, so number 13, calculate the mass. By the way, if there's problems like that, and I will explain them to you quite right, and that'll be adjusted for. But I'll get that one done for you. Okay, number 13. Calculate the mass percent of carbon, nitrogen, oxygen, and acetamide. Okay, so acetamide is C2H5NO. And what I want to do is find the percent composition of each element. Okay, so what I do is I find the total mass. So what's the mass? Okay, so the molar mass, so it's going to be 24 plus 5 plus 14 plus 16, 35, 59 grams. 59 grams, let's say. Okay. So total mass is 59 grams. The amount of carbon is going to be 2 times 12 all over 59 times 100. The amount of hydrogen is going to be 5 times 1 all over 59 times 100. The amount of nitrogen is going to be 1 times 14 divided by 59 times 100. And the amount of oxygen is going to be 16 times 1 all over 59 times 100. Okay. Hopefully you see what I've done here. So 24 divided by 59 is times 100.
40.7%.
40.7%. The amount of hydrogen is going to be 5 divided by 59, which is roughly 11 point. No, not 11.
8.5%.
8.5%. 14 divided by 59 divided by times 100.
20,
What is it?
23.7%.
23.7%. And then finally, oxygen is going to be 16 divided by 59 times 100.
27.1.
27.1%. Okay, if you add these all up, they should be pretty close to 100. Okay. Like 41, 50, 75, yeah. Okay. All right, number 14 says I have 50.51 grams of sample of phosphorus and chlorine. It's decomposed. The products end up giving me 11.39 phosphorus. And what is the empirical formula? So you've got what A and B are unknowns, and we're not really worried about those. And what happens is decomposes into phosphorus and chlorine. And we don't really have to worry about their chemical formulas. So you start out with 50.51 grams of this. And then you end up with 11.39 grams of this. Now we can figure this guy out. What is this going to be? So this is, now we can, okay? Because the sum of these two guys has to equal the sum of that side. So 50.51 subtract 11.39,
39.12.
39.12?
Yeah.
Okay. All right. Now I want to figure out the empirical formula. Well, I got grams. Now I can just figure out moles. Okay, so I divide by the molar masses. This is someone we don't worry about. So divide by 31 and divide by 35 point, I'm going to say 35.5. If you want to be really precise, you use sig figs and everything, but it turns out usually you end up getting whole numbers that are real close. And on a test, I would let you know what to do with the sig figs. Okay, 11.39 divided by 31 is,
0.367.
so that's how many moles of phosphorus are. And then 39.12 divided by 35.5.
1.10.
Check that number again. What's that? It's 11. .367. 39. Okay. I don't like these numbers as much as I would like. Okay, so we're gonna get one chlorine. No. Okay. Oh yeah, this will work out. So we divide this number into this number. So we divide the small number into both of them. That's what it's wrong. So divide both by 0.367. How many phosphorus is that then? 1. I can do that. Pretty smart. And do the same. 1.1 divided by 0.367 is
Almost 30.
Almost
It's 2.99.
okay. So it's 3. Okay, so it's PCl3. At least that's the empirical formula. And they don't ask us any other. They don't give us any other information to figure out if it's not. That probably is the molecular formula too. Okay. Number 15. You have 2.5 grams of oxide of mercury. It is decomposed into elements. By heating, 2.405 grams of mercury are produced. Calculate the empirical formula. Same idea. So AgX OY, and we'll go into Ag plus YO. Okay. They start out with 2.500 grams, and we end up getting 2.405 grams of mercury, and what's left over, you can figure this guy out. And what number is that? 0.0095? What's the difference between these two? 0.95?
Yep.
Okay. We divide both of these by their respective molar masses. Mercury is 200.6. Oxygen is 16. Okay. So 2.405 is how many moles? So we're going moles.
The 0.011.
Okay, so that's moles of mercury. And 0.095 divided by 16.
0.006.
Go one more digit. Or is it
9.
9.
Or will it be 1 now? Got rounded. It'd be 59. 0059.
Okay. Okay, so you divide this guy by that. So we divide both of them by the smallest number, 0.0059. 0.0059. This number is going to be 1 oxygen. And 0.011 divided by 0.0059 is
1.86.
1.86. Which is almost 2. I think if I got that number, I would use the more exact precision, because that's a little bit far off of a whole number, but I'm gonna suspect that it's actually 2, closer to 2. Okay, so. I'm guessing it's that. If you get a number that's, if it's like 1 point, like that number, I would definitely redo it with more precise numbers, using all the digits that the periodic table gives you, and using sig figs. And then if you got something like that, I don't know. I don't know if I feel comfortable about rounding it up to 2, because it's a little bit far off than I would like it to be. So the ones I'll give you on the test will give you a whole number. We'll give you close to a whole number. Closer than that, I would hope. Okay, next problem is benzamide. We give you the percent composition, and we want to figure out the empirical formula. Okay. So 69.40 divided by 12, because it's carbon. 5.825 divided by 1, and it's hydrogen. 13.21 divided by 16 is oxygen, and then 11.57 divided by 14 as is nitrogen. Okay, so we have grams. Remember, we can do, if you give percent, you're just going to assume that's out of 100 grams, and don't worry about percents, and have it in terms of grams. So 69.4 divided by 12 is 5 point something.
5.78.
Moles of carbon. 5.875 moles of hydrogen. 13.21 divided by 16.
0.826.
6 moles. And 11.57 divided by 14 is
.826.
All right, so we're gonna divide by the smallest number, which is both of these. So when I do that, I get 1 oxygen, and I get 1 nitrogen. Okay, how many hydrogens do you get? 5.87 divided by 0.826. What is it?
7.
Okay, 7 hydrogens
7 carbons.
and 7 carbons. C7, H7, O-N. Okay, and the last one is a component. A protein called serine has an approximate molar mass of 100 grams per mole. What is the empirical and molecular fluorine of serine? Okay, let's do it again. So 34.95. Okay, we're in percent, so we can think about it in terms of grams. So it's carbon, so divided by 12. 6.844 divided by 1, because it's hydrogen. .56 divided by 16, because it's oxygen. And the last guy is 13.59 divided by 14, because it's nitrogen. All right. 34.95 divided by 12 is almost
2.91.
2.91 moles of carbon. So these are moles, these are grams. This is 6.844 hydrogens. 46.46 divided by 16 is
2.91.
2.91, that's helpful. And then 13.59 divided by 14 and
971.
0.71. Okay, divide each one of them by 0.971. Because it's the smallest number. You get 1 nitrogen. How many carbons you get? I guess it's 3. How many oxygens you get? I guess it's 7. How many oxygens? 3 again. And there you go. Now, okay, so it's C3, H7, O3, N. All right. Add those all up, and then that'll be add up their mass. That's the empirical formula mass. Compare that to molar mass, which is almost 100, and see if this is the empirical formula. All right. So it's going to be 3 times 12 plus 7 plus 3 times 16 plus 14. 43, 91, 104. 104. Okay, so So it says it's about 100, and I'd say that's close enough. So the empirical formula and the molecular formula are the same. Okay. So if you understand what we're doing, a couple of things we're sort of jumping to the chase here without doing the triangles or doing any conversions. Is number one. When you get percent mass, and what you can do is you can assume that's grams, because it's saying is that you'll have so many grams out of 100 grams. Okay. So you don't have to change percent composition to you don't have to change it to anything else. You just figure out directly how many moles it is. The other thing is that when you figure out moles, in terms of the triangle, what you're always doing is you're dividing the grams up into moles by their molar mass. So I just go ahead and say divide without worrying about all kinds of things that cross out, things like that. Now I know there are some people out there, that say you can't, you're missing a lot of precision and you're messing things up. But if you understand the concept, that's the key. The keys are the concepts. It's not really the method, it's the concept. And most of the times, the numbers that you'll get, they'll be whole numbers, real close to whole numbers. So we're not going to give you, when I used to get these problems, I'd get a number like this, and I go, oh, I got to get all whole numbers. So what I do, I multiply everything by 100, okay? And that gave me whole numbers, okay? But you want to get small whole numbers. You don't want to get huge whole numbers. If you get, when you do these and you get, like on the one problem where you got 1.86, that's a problem. I would really take some time to figure out what's going on with that one. Okay. Okay, ready for a test? No. Maybe today. All right, so we got another worksheet with stoichiometry. This is what we use is that, why don't you guys try to do the, right now, why don't you try to do the first two? So basic stoichiometry. Go ahead and try to do the first two.